Thank you very much for inviting me. A bunch of familiar faces, but a bunch of faces that I met before. So thank you all for coming up. Um, I'll try to look at the chat section. You can wave hands or something if I don't get to the chat and answer questions. So do I hit the power's going? Does that work?
Sometimes if it's unclicked.
There we go. So as I said in the introduction, I've been working on pegmatites for a while. Part of my PhD thesis was non-sila pegmatite in Thailand. That's 1986, and my Land Rover was about 20 or 30 years older than that. Um, but it was a fun pegmatite to work on in the layered apelite pegmatite complex. So it's been working on pegmatites since 1986. In part, I made my name through doing actually experimental work. I had the pleasure and fortune to work in Orléans, in France, where I started doing experiments. And then I moved to Bayreuth in Germany, and then I set up my own lab, first in Waterloo and then University of Western Ontario. And I did a lot of experiments, mostly on metal solubility in granitic melts, pegmatite melts. I retired from Western. I'm still an adjunct professor and professor emeritus. Still have got students like in the back. So I still have my fingers in academics, but since 2022, I moved to KoBold Metals. All of you know Peter Lightfoot. You can blame Peter. He said, "Why don't you go ask Bob what he wants to work with you guys?" And it's been a lot of fun. I don't. We have one university professor here, anyway. It was refreshing because at least initially, all they asked me to do was think. I didn't have to do grant proposals. I just had to think, and so my first task really was looking at the mineral system and just thinking about mineral system and have a sort of a companion talk on the lithium cycle from the oceans through to the mantle. I won't go into that this time, but I spent a lot of time thinking about pegmatites, how they work, what controls them, and I'll discuss a little bit of that. I like this slogan as well. So a lot of people think of KoBold as, oh, you're one of these AI companies and like you're eggheads and you don't know anything about rocks. It's AI and HI. The human intelligence, if you don't have that, the AI doesn't mean anything. So very strongly on integrating with how geologists think, integrating how data scientists think, and trying to test different hypotheses. So for those of you that aren't that familiar with mineral systems, I'm sure most of you are. A mineral system considers all of the geological factors that control the generation and preservation of a mineral deposit. And I'm going to just look at a couple of thoughts on each one of these squares here. So the tectonic setting, regional scale controls, igneous processes, transport, trap, and post-magmatic processes. So this won't be a terribly long talk. I designed it to be roughly a half an hour or so, but certainly we've got lots of time. So if there's any questions, don't hesitate to interrupt me and go, "Whoa, what? I don't understand what you're talking about." Or Dan's here, so go, Dan. He'll say, Bob, I don't believe that. What? Have you thought of it this way?" So don't hesitate to interrupt him. And it should be a discussion. If you have contrary views, don't hesitate to express your contrary views, and we can get a bit of a discussion going on what some of the evidence means. So, in my view, and the view of many others, I believe that lithium pegmatite are orogenic deposits. And there's an awful lot of similarities between orogenic gold deposits and orogenic pegmatite deposits. They're located along major shear zones, structural breaks. There's a lot of the structural controls of pegmatites are similar to what the structural controls of orogenic gold deposits are. And if you look at the timing, so on this diagram here, the colored bars are assemblies of supercontinents, Pangaea, Gondwana, Rodinia, etc. And then the smaller histograms are the ages of pegmatites. And the lithium pegmatites are clearly overall associated with these assemblages of supercontinents. But the other thing that is pretty consistent, particularly if you look at this period of, they're late tectonic. So we have an orogenic event where you'll have a collision, an assembly of a craton, and it's at the latest stage when we start to get relaxation. It can still be compressional, but you can get transgression, you can get things opening up. It's invariably the lithium pegmatites are coming in at the end of that tectonic cycle of the assembly of the supercontinents. We see that in many cases. So timing of the pegmatites is typically syn to late kinematic. Can pegmatites be pre-kinematic? They can, but usually they're syn to late. Okay, we'll take a look at one example of a tectonic setting. This is Namaqualand in Namibia. And you can see that we've got the Congo craton, Kalahari craton, and then marginal to those craton or collision belts. Gabarin here is where Monono is, which is the world's largest lithium pegmatite, associated with the collisions, the assembly during I always get it mixed up. I think this is Rodinia. And then the Namaqualand origin is the same time. So it's the same date. The barren origins are much, much younger. That's around 500 million years. So if we look at the Orange River Shield, which is in both South Africa and in Namibia, we can see that the ages are 1038 to 968. The actual orogenic event is 1400 to 1000. So this again is typical of pegmatite belts, that they're late orogenic. The other thing that I believe is true is there's about a 20 million year age difference in different pegmatites that are dating. And the ages are about plus or minus 5 million years. And I think that these are also typical of many pegmatite fields. How do I interpret it? It's that tectonics is not static, it's dynamic. So you get pulses. So you can get, particularly at these end stages of tectonism, you'll get pulses of heat that are coming up from the magma, from the mantle, causing pulses of different heating events so that we can get different pegmatite intrusions at that late tectonic stage that span a 20 to 40 million year time event. And so that I think those age dates are actually real, that the 20 million years, that's how long pegmatites were being in place at the end of that particular tectonic cycle. So the implication of the age dates is multiple periods of melting, multiple emplacements at the end of an orogenic cycle. It's not everything was emplaced at 2685 plus or minus 10. It doesn't work that way. It's more like a 20 to 40 million year age difference of emplacement of pegmatites. And commonly what we'll see is there'll be multiple generations. Sometimes one generation is mineralized and another generation isn't mineralized, and maybe the older one or maybe the younger one, but there'll be multiple generations and not all of those generations are mineralized. Multiple generations is certainly something that appears to happen globally. Looking now at a regional scale, the metamorphic grade, in my view, is very important, and Cherney noted that. If you look at this map here, so we've got pressure and temperature. So 50 degrees C is a high temperature, low pressure geotherm. 25 degrees C is fairly average, low temperature, low pressure, average geothermy. And Cherney noted that he called them Abakumba metamorphism, which is kind of an old name for a metamorphism. Now we just call it high temperature, low pressure. that most pegmatites, mineralized pegmatites, were associated with this abacuma metamorphism. Why is that the way it is? Also on this is the boundary between petalite and spodumene. You can see this green polygon is what I've drawn, and maybe it's exaggerating the truth, maybe not, but you can see that there's a lot more in the spodumene field than the petalite field, which is why we probably have a lot more spodumene pegmatites than petalite pegmatites. We have both, but spodumene is more common. So with the petalite, you have to have 50 degree per kilometer geotherm, whereas if you're more, let's say 40, 35, you're going to be going through the spodumene feature. So why is that important? Well, similar to gold deposits, you need fractures. If you have ductile rocks don't fracture easily. You have to have a high strain rate to make a ductile rock fracture. We want to open up spaces. If all we're going to do is open up a space that's 1 meter wide, you're never going to have a mine. We're looking for pegmatites that are 30, better yet, 100 meters thick. How do you get a 100-meter thick pegmatite? You have to have the rock open up. How do you get the rock open up? It has to be brittle, excuse me. How do you get brittle rocks? You get brittle rocks with high geothermal gradients so that you're more in the brittle. It can still be brittle ductile, but you're more in the brittle domain than you are in the ductile domain. So when we get it to the high pressure, certainly granulite, it's hard to form a dike that's 100 meters across in a granulite terrain because just the rocks are just too ductile. So to me and others, the metamorphic grade is really important. And for instance, when you look at these phone calls, a lot of people will look at, do we have, say, cordierite andalusite grade metamorphism? When we're starting to get up into the upper amphibolite, it's probably too high a pressure. We can still get pegmatites, but my definition of lithium pegmatite is something that's worth money. We can mine it. A pegmatite that's got no more minerals in it is just a pegmatite. I'm interested in the ones that are worth money, the economic ones. The economic ones have to be thickness of greater than 10 meters. How do you get that? It's being controlled by the rheology of the host rock, and it's much more favorable at high temperature, low pressure metamorphic conditions. So next I'm going to move on just to a little bit. I'm thinking about lithium. What minerals contain lithium other than the lithium ore minerals? So if we look, I know this diagram by Rare's guy, just ionic radius, and then the lines are field strength, so charge to ionic radius ratio. You can see at the top, the ionic radius of lithium is very, very similar to magnesium. So lithium likes to substitute for magnesium. And you go, oh, okay, well, olivine should have lots of lithium in it. No, because it's a 1+ substituting for a 2+. So in order for that to work, you have to have coupled substitutions. Now, pyroxene, at least you've got a chance with a coupled substitution because you can have Al3+ in a pyroxene, clinopyroxene. Whereas the best minerals are the micas, because the micas have both tetrahedral and octahedral aluminum, tetrahedral and octahedral silicon, so we can have coupled substitution mechanisms where the charge balance of lithium can be maintained. So here's just a couple of examples where you've got an octahedral aluminum plus an octahedral vacancy goes for an octahedral magnesium and an octahedral lithium. Number of is respected, number of charge respected. This one I think is maybe a little more common, a phengitic substitution where we have octahedral lithium, tetrahedral silicon substituted for octahedral aluminum and tetrahedral aluminum. So just based on a theoretical consideration, the micas are where most of the lithium is in the rock. And the reason why they're there, chlorite is another example. You can get lots of lithium in a chlorite because the chlorite has coupled substitutions. So it likes to go where magnesium goes, but it has to go into a mineral that has multiple sites with multiple valences, so you can get coupled substitutions to accommodate that lithium. So I like this diagram. This was a study by Negrel et al., and this was a continental scale soil survey of Europe. It's really fascinating. You look at clay and mica content, lithium, boom. It's, it's correlated. The lithium in the soil samples is just being controlled by the amount of clay. But the other thing that's interesting here is if you look at, yes, the granite samples are a little bit higher. If you look at the greenstones, the granite, this is all the geology below the soil samples. The greenstones can have just as much lithium in them as long as they've got the clays. So if you've got a greenstone, it's got lots of chloride in it, the chloride will take up the lithium, substituting for the magnesium in the chloride. So clearly, you can see at a continent scale, even though the rocks, the shifts, the granites, the greenstones, these, they're all forming the same trend. It's the clays that are controlling the lithium content, in this case of the soil, but it's also of the rocks. So another constraint now is igneous petrology, which is a subject near and dear to my heart. What this diagram shows is that depending on the temperature, you have to be about 5,000 to 10,000 ppm. If you're below 5,000 ppm, you won't form spodumene. This is the solubility of spodumene. So if you have a melt with 4,000 ppm lithium in it, you won't get spodumene. There's not enough lithium to form the mineral spodumene. You're not saturated in spodumene. So anytime you have a lithium pegmatite that has spodumene in it, and the numbers are virtually identical for petalite, really doesn't matter which the phase is. If you have a magma that is saturated in petalite or spodumene, it had to have had on the order of at least 5,000 ppm lithium in it, and possibly up to 10%. Another sort of a tangential to this, most people don't know what 5,000 ppm lithium is in terms of weight percent. Does anybody, well, some couple of people in this room know, what's the average grade of a lithium pegmatite being mined? They're about 1 to 1.5%. Guess what? That's 5,000 to 10,000 ppm. Lithium is a really light element. By the time you make an oxide out of it, this is ppm versus oxide. Those numbers are actually the grade of most spodumene pegmatites. To me, what that's telling me is that certainly for the albite spodumene type, that these are homogeneous pegmatites, they came in nearly saturated in spodumene, and then boom, they crystallized because the melt of the whole rock composition is similar to what spodumene solubility in the melt is. And to me, again, that indicates that the melts were nearly saturated in spodumene by the time they were emplaced, and then cooling resulted in crystallization. So next, what we're going to do is just look at, there were two theories, and people, including myself, have started questioning those theories. I'll also, a little bit of context. We've been studying orogenic gold and porphyry copper for well over 100 years. The number of studies of lithium pegmatites is minute compared to the number of studies of gold deposits and copper deposits. So it's not going to be surprising that the sophistication of the models that are being generated to explain this particular gold deposit is nowhere as sophisticated as the porphyry coppers or gold. Orders of magnitude less people working on it, orders of magnitude less deposits as far as that goes as well, less examples. So until recently, there were really two competing models of how lithium pegmatites, or pegmatites in general, but lithium pegmatites in particular, how these deposit forms. So the first one is called an anatectic model. I actually sort of disagree with these names. If you think of a granite, if you melt a granite, that's anatexis. So all granites are anatectic, and all granites undergo fractional crystallization. Nonetheless, we have an anatectic model and a fractional crystallization model. So it has to be in between the two because both processes happen to make a granite. So in this case, we have zone melting We see in nature, we see bond-type granites, 2-micron granites, muscovite granites, pegmatite granites, pegmatitic granites, and pegmatite. We see that formation. Not as good as that, but we see versions of that. And the argument is that low degrees of partial melting produce the most lithium, beryllium, cesium, tantalum rich units. So low degrees of partial melting, and you get pegmatites that are rich in those elements. I'll show you in the next slide. It just doesn't work that way. So the previous slide, I said we need 5 to 10,000 ppm. So we know something about partition coefficients, what the lithium is in. The lithium is in the micas, it's in the biotite, it's in the muscovite. If we melt a rock that has biotite or muscovite in it, we know what the partitions are. We can know what percentage melting is. We're nowhere near 5 to 10,000 ppm lithium. So even if you believe in an anatectic model, that there's no big granite crouton that's crystallized in fractional crystallization, with the anatectic model, we still need fractional crystallization. You can't generate a melt with 5 to 10,000 ppm simply by melting a crystal source. I'll show some more evidence of that in a subsequent slide. So here are just some more information on the anatectic model. We can see that if you compare biotite to muscovite, and there are very few of these studies where people have taken metamorphic rocks and seen what the deportment, what the distribution of lithium is between different phases. There's only a handful of these studies, but this is one of them. And you can see that there's about an order of magnitude more lithium in the biotite than there is in the muscovite. Same thing is going to hold true for the cesium. Really makes that cesium. Cordierite can have significant lithium in it. Staurolite can also have significant lithium in it. And I'll show you in the next slides that that's true, but actually, if you look at the phase equilibrium of the partial melting, the gray wackies are more favored over the peelites. The cordierite and the staurolites are in the peelites, but the melts that are produced from melting a gray wacky have more lithium in them than the melts that are produced from melting a peelite. So there are a few examples around the world where cordierite is in the metamorphic rock, and there's certainly lithium in that cordierite, and people have argued that that's what the source is, and certainly there is lithium in cordierite, but gray wackies are a better source than for metamorphic rocks. Gray wackies are a better source than the peelites. Most of what's controlling the lithium is biotite and, to a lesser extent, muscovite. Muscovite's interesting though, because if you think about it this way, if you have a granite and you start crystallizing, where's the last one you'll think about crystal? You start crystallizing feldspars, and you'll have quartz and feldspars, and then eventually, usually it's the micas that are the last to crystallize. You know, even muscovite, it's the last to crystallize out into the biotite. The knowledge inverts. We heat that and upwards to crystalline melt, so we get muscovite. The muscovite melt first, and then after all the muscovite's consumed, you need another step of heat to then start melting out the biotite. But if you look at the partition coefficients, it's actually it's compatible in the biotite. So this idea of partial melts to be really, really low and everything within a partition is the melt. No, actually, the lithium is going to be more strongly held by the biotite than it is in the melt. But we can do calculations to see how there's actually a progression of biotite. It's a recent paper where they look at the partition coefficients themselves depend on the composition of the biotite. We all know that as you metamorphose rocks, you'll change the FeMg and you'll become more and more Mg rich as you go up temperature, and the partition coefficients actually change as you go up temperature as well. So things aren't quite as simple as this. They're more complicated than that. But the biotite is where most of the lithium is coming from. Before I go on to that modeling, whoops, I thought I had whoops, no, I've got too many. I'm going too fast here. This is the one that I wanted. So I find this diagram is also, I think, really instructive. So when we go to places like Zimbabwe, there aren't any big sedimentary belts. So if the gray whack is supposed to be the source, there aren't gray wackies there. And to a certain extent, we also see this in Australia. There's a recent paper published by some Australian guys in the survey that said, look, we think the sources are igneous. And if you start looking at it, so you've got S-type granites, I-type granites, A-type granites. I hate the word S-type, I-type, and A-type, because if you melt something that's a sedimentary or igneous source, it really doesn't matter. But if you look at the distribution of lithium, log lithium now in the different types of granites, it's yes, the S-type tend to have more lithium, but it's really not convincingly, it's not a huge shift. So if you melt an I-type granite, the first thing that you will melt are the limits. And that's where the lithium is. So you don't necessarily have to have a sedimentary source to produce a paraluminous melt. You can melt an I-type granite and produce a paraluminous melt that will have lithium in it because you're melting the biotite. So we're not restricted to sediments. I think by and large, most pegmatites probably are the result of melting metasedimentary rocks, but not all. There are many cases around the world where we believe the origin of those pegmatites are melting igneous rocks, not melting sedimentary rocks. The important part is the abundance of mica in that source rock. Hornblende, forget it. We don't have any lithium. Biotite's good. You melt it, we're gonna make lithium. Oops, what have I done? You have to try that. Here we go. So this is the modeling now. Fortunately, I pushed him. Lot Koopmans did his PhD, and I pushed him to come. That's a KoBold. We're very lucky to have him. I worked with Lot on this. So this is the modeling that he did. So these aren't physical experiments, they're computer experiments, they're phase equilibrium experiments using metamorphic software. And you can see is that there's a bunch of stars and a bunch of different colors. You can see the gray lacquer at 8 kilobars versus the P line at 8 kilobars. There's more lithium in the gray lacquer. Similarly to 3 kilobars, there's more lithium in the gray one. One of the things that we model is we can argue about the number, but there's certainly a fixed number or a number that's over a range. You have to have a certain amount of melt to extract. If you have 1% melt, if I took a column of sand and I put a drop of water on it, would you expect to get a drop of water out of it? No, of course you didn't. The water is going to absorb. That's called wetting grain balance. You have to have a certain minimum amount of melt produced in order for that melt to move. So if you only have 1% melt, you have 1 or 2% melt, but you're never going to extract it out of the rock. Even if you have shearing, you won't extract it out of the rock. So the number we use a literature value by consensus in the literature. It doesn't mean it's necessarily exactly true. We use 7%. So you have to produce 7% melt in order to be extracted. You can't extract the melt, and you can't undergo fractional crystallization and place it anymore. So there's a minimum amount of melt that has to be produced. That's what these stars are in the end. So if we extract take a metasedimentary rock, either a gray lacquer or a peelite with about 125 ppm, that's global average, not a special rock. It doesn't have to be, a rock that had started out with 3,000 ppm lithium in it, and that's what we melted. It's like, no, this is just a gray wacky or a peelite with 125 ppm global average lithium. If we melt that, depending on the temperature, we can see that we actually melt them. This is where the muscle comes in first, and then we start to melt out the biotite, and the lithium concentration in the melt increases as biotite is progressively melted out of that rock. So we can generate in one stage melts with an up to 800 degrees C, 200 to 500 ppm. That's nowhere near lithium saturation. Remember, we needed the 5,000 ppm. Okay. I seem to be skipping over stuff in a minute. Well, I thought I had another diagram in there. I guess I don't. So what we propose is, maybe I've got my slides mixed up, and maybe I'm going to present this later on. So what we proposed is that you melt the rock. Doesn't matter whether it's an igneous rock or a metamorphic rock. You melt it, you're going to produce a melt with up to 500 ppm, 200 to 500 ppm lithium. That crystallizes. Go back to that slide where it says we have a 20 million year, 40 million year range in uses of pegmatite, which is reflecting pulses, periodic pulses of heat over 20 to 40 million years. So we can melt that rock and produce a new melt, except now the starting is, instead of starting at 125, we're starting at 212. So by remelting the previously crystallized granite, we're producing melt with progressively higher and higher amounts of lithium. And you can do that only 1 or 2 cycles. You can generate melts that, with a bit of fractional crystallization, will easily attain the 5,000 to 10,000 ppm lithium. So we believe that it's not a single stage process. It's a matter of melting a source. The source doesn't have to be particularly enriched. Melting that source, crystallizing that granite, new heat pulse comes in, melt that granite, it moves on, and it crystallizes either directly the lithium pegmatite, this is crystallization, or there's an undistributed remelting. We have evidence in the geological record that we have periods of heat that are 20 to 40 million years in length at the end of orogenic cycles. So the next problem, actually, I think I do know where that slide is now. We'll be seeing it. The next model is called fractional crystallization. Ghost Lake batholith. Many people in this room have probably seen the Ghost Lake batholith just outside of Dryden. We see these zones. So there's a big batholith. There's this nice granitic pegmatite here, and then the zonation of pegmatite away from that. So there are other places where we see the same thing. So we see this zonation, and the zonation is consistent with fractional crystallization. Question is that really how the lithium pegmatites are generated? So if we look at a fractional crystallization model, this happens to be a paper by Hulsbach looking at pegmatites of Rwanda, but there are many other studies that find similar results. That with K-feldspar and with muscovite, rubidium is more incompatible than biotite is. So as you fractionally crystallize a K-feldspar, the KRB ratio goes down. As you fractionally crystallize a muscovite, the KRB ratio goes down. So the curves are the model and the symbols are the points. But if you do the fractional crystallization modeling, you need 0.99. So now you have to ask yourself, is 99% fractional crystallization a reasonable physical process? And we make the argument, no, it's not a reasonable physical process. So in this model here, similar to the 7% that we used melts to be extracted during melting. Here we're using a slightly different number. Again, it's from literature, from people that are experts in these things. We have something called the barnacle locking threshold. And we know instinctively, we know that if you have a bunch of crystals, right? If you had a bunch of honey and you threw in a bunch of chocolate, by the time you go up to 90% chocolate and 10% honey, the thing is rigid, it won't move. The honey can't flow. That's crystal locking. So there's a finite value to which fractional crystallization doesn't work anymore. Fractional crystallization only works if you're separating the liquid from the crystals. So there has to be a finite value. Again, we used a literature value of about 15%, let's say, or sorry, 25%. We said, well, even if it's extreme fractionation, and we're at 10%, because the models are rough guesses, still by taking these values here, where those stars in the first diagram, that previous diagram, the up to 2 to 400 ppm. When we fractional crystallize it, by the time we get up to 90% fractional crystallization, we're still only at 3 to 4,000 ppm lithium. So fractional crystallization doesn't seem to work. So we propose this two-step model where we have an enriched sediment, 125 ppm, we melt it, then we crystallize the granite, then we melt that granite, and here the direct melt of this granite is on the order of 2,000 to 3 to 4,000 ppm. Then you need very little fractional crystallization of that melt to get to your 5,000 ppm. So we criticize both the previous existing models. We think that both are right in some extent, that anatexis is an important process, it has to occur. And fractional crystallization is an important process, it has to occur. But 99% fractional crystallization is probably not reasonable. And one hypothesis to explain the data is a multiple step modeling, which is essentially ground distillation here. Fractional crystal melting, crystallization, melting, it's progressive, it's really fractional melting and crystallization for multiple melting models. Okay, let's look at transport now. For many of you, you'll be familiar with this map. This is the Yilgarn in Australia. If I told you you were looking at gold distribution, you'd go, yeah. You're not. Actually, you're looking, the red dots, government database of where pegmatites are intersecting drill holes. And there's a really strong correlation between these things. Exactly the same way that you see with gold deposits, except there's a heck of a lot, an order of magnitude more data for gold deposits than there is for lithium pegmatites. So shear zones seem to be conduits for pegmatites. So there's actually, we've done statistics on it, and there is a statistic correlation between the occurrence of gold deposits and the occurrence of lithium pegmatites, but that doesn't mean they're cogenetic. So the gold deposits don't have to be the same age, they can have completely different sources, they're just using the same conduits. Gold deposits use shear zone as conduits, pegmatites use as conduits. So it's not surprising that we get gold deposits and shear and pegmatites associated with major shear zones. And commonly they're at the edges of subcontinental divisions, terrains. That really doesn't show it here, but they're definitely structurally controlled. So the conduits are by and large shear zones, or fractures. Certainly they have to have high permeability. And then the trap is also similar to gold deposits. We have structural. So this is a model of Tanko that Paul Kramer did. We can see these nice on echelon dikes cross-cutting a gabbro raft in Tanko, and the model is that it's transpressional and you're getting opening up in a particular band of the shear zone, similar to what we see a dilatant zone in gold deposits. So there's a lot of structural similarities between, they're not identical, but there's a lot of structural similarities between gold deposits and pegmatites. Whereas we're out there looking for dilatant zones because the dilatant zones are where the thicker dikes are going to be. Excuse me. Water anyway. Put it on the ice. Yeah, I'm drinking it all. So this is a nice USGS photo. 1916, there you can see first, and that's spodumene crystal. How the heck do we get these big spodumene crystals? So the current paradigm, we don't have all of the details, but we have all of its components pretty much understood. Granitic pegmatites have high concentrations of fluxing elements. So what's a flux? Anybody raise your hand if you haven't done any welding? Nobody done any welding? Well, what's flux? The flux levels melting, right? So that's what these things do. The flux, they lower the melting temperature of the ground. So you get temperatures at lower and lower with increase the fluxes. Water is a great flux, but lithium, fluorine, boron, phosphorus are also fluxes. So those fluxes decrease the solidus temperatures. The other thing that they do is they increase diffusivities. So you're changing the viscosity and you're increasing the diffusivities. And another thing that the fluxes do is they delay nucleation. So if you have, say, a granite with water in it, you might have to go, I love this. So what temperature does water freeze at? Anybody? No. You can take water and put it in 0 degrees, it'll never, ever freeze. Ever. It has to be below the nucleation temperature. You have to be below the solidus. You have to overstep it in order to provide kinetic energy crystals. So what happens is when you have water as a flux, you may only have to have a 20-degree supercooling to crystallize itself for our course. Where when you add the fluorine and the lithium, it becomes greater. You need a larger decrease in temperature in order to nucleate crystals. So the fluxes they increase diffusivities, but they also increase metastability. You have to have a larger supersaturation temperature in order to crystallize it. So as a result of that, we end up with actually fast crystal growth rates as a result of supersaturation as a result of undercooling. And that's why we believe that there are these large crystals. Why are they large? Because the diffusivities are fast enough that you can grow large crystals. If the diffusivities are too slow, the crystal growth will just stop. But if the diffusivities are fast enough, you can grow large crystals. And you have this supercooling. So most pegmatite textures are related to supersaturation or supercooling phenomena. I'm near the end of my talk now, so we've gone through most of the steps of the mineral system model. The last step is post-magmatic processes, and these are most important for mineral processing. So on the left-hand side, this was work by Johannes. He's actually a colleague as well at KoBold. This is from his PhD. And where you get alteration of spodumene. This doesn't look that bad. You still got good spodumene. What happens is when you put that, I'll back up. So spodumene itself, surprisingly, is insoluble. So there's something called calcination. For those of you that know a little bit of metallurgy, calcination is you heat something up to high temperature. So if you heat spodumene up to 1,000 degrees C, it goes from alpha spodumene to beta spodumene. And when it goes to beta spodumene, if alpha spodumene, you put it in sulfuric acid, nothing happens. Beta spodumene, it changes its structure. You think of entropy as you heat something up, things become more random. You're changing the crystal structure. So the beta spodumene is then soluble with high temperature sulfuric acid. That's how they process most spodumene ores. Undergoes this calcination. To get the lithium out of solution is another story. That's lithium hydroxide, carbonate, all that stuff. But just to get the lithium in a leachable form, you have to heat it up. Guess what happens when you heat this up for 1,000? Muscovites melt first. So the muscovites melt and then provide the glass coating on top of the spodumene rays, which drastically decreases your recovery rates. Because you just coated all of the ore minerals. Now you're not recovering. So the real problem with alteration of spodumene is metallurgical. So if you've got a property, right, and somebody's reporting, well, it's 1.2% Ll2O, that really looks good. If you haven't done any studies of the spodumene, if it's not fresh, it's a problem. You won't get it through the mill. Like you'll get it through the mill, but you'll either have to crush it to less than 100 microns, that's really expensive, or if you try to heat it, it's going to gum up because the muscovite is going to form of glass and form these glass around coatings, thin layers around the spodumene grains. So alteration is a big problem in mineral processing for spodumene. This second one, here's a great example. This is some work on Tanko. And there's a texture called SPDA, which is a short form for spodumene quartz integrates. And here, it's not so much a problem with the previous one where heating it up to 1,000 degrees is going to change things. It's like, no, you look at the scale here, 500 microns. So this micro squee, Tanka was particularly interested on us working on this. If you have squee that's say on the centimeter or millimeter size, hey, no problem, because we're crushing our rock down to whatever size, 2 millimeters or whatever size the crushing is going to. The one on the right, you can't crush that to 2 millimeters. You'll get a terrible recovery rate because of this micro squeeze. So again, when you have the pegmatite, you have to do some geometallurgical work on it to know whether it's altered, to know whether there's squeeze. All of those things are important in terms of recovery rates. And then I guess I didn't put in the last slide. One last slide was just in terms of preservation. Well, we're looking at pretty much from green schist to maybe middle amphibolite. So if you're looking at something like the granule, it's like, no, there's been too much uplift. There were any pegmatites, they're all gone, right? We're looking at the Abitibi or other superior provinces where you've got the right metamorphic grade that's preserved. So the depth of emplacement is reflected in, on surface. What's the metamorphic grade? So going back to that metamorphic gradient. So post-magmatic processes and preservations, and that's it. Oops, sorry, one more. So I did this work. I'll digress with a little story. I did this work on the Dibs pegmatite, which is just outside of Tanko. It's about 5 kilometers, 2 kilometers. I can't remember. Maybe you know where the Dibs is. It's 2 to 5 kilometers just to the east of Tanko, northeast. And so I was working with Tanko, and I had this epiphany. So at that time, they were getting false positive anomalies. And they didn't really understand why they were getting false positive anomalies when they were doing their soil geochemistry. And as I said, I had this epiphany. Why were they getting false positive anomalies? They're getting false positive anomalies. Let's go back to something I said right at the beginning of the talk. Lithium substitutes for magnesium, blah, 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 blah. You have chloride along fractures. The lithium is going to be in the chloride. So when you have white greenstone delta, you know that there's not chloride along fractures. Right? So that can cause a false positive anomaly. And so then I got the epiphany was igneous petrologists have it wrong. What does an igneous petrologist do? You take a rock, you saw off all the fractures, and then you go analyze the rock. It's like you take a rock, you saw off all the fractures, keep the fractures, and throw the rest of the rock. And analyze those fractures. And what are the fractures telling us? So that's what's showing me here. Is there's 4 rock values, which is the blue triangles. So I did analyze the rock. I didn't show it. And then I analyzed the fractures and metamorphic minerals, and we can see that the biotite, it's got far most amount of the thing I like about this diagram. You can see how it curves like that. So they just stopped in another gather. So everything that's white is gathered. And the Dibs pegmatite there is about 40 meters thick. As soon as I saw that, we got on the phone to Tanko and said, you got to go back and deepen that drill hole. There's another pegmatite underneath it. Those values are going up again. And sure enough, they went in. It's a technical success. They didn't find great mineralization, but yes, they found enough pegmatite right down here. You saw in the Tanko pegmatite that I showed you those on echelon pegmatite dikes, right? There was another on echelon pegmatite dike below it. And what we were able to show is that this is a straight dispersion halo around a pegmatite. And It's being driven by fluid flow in fractures. And what really surprised me, I could show you a thin section and you go, this is a metamorphic rock. But these ones, the contents of lithium in the biotite, they look like metamorphic biotites. This is a tremolite biotite plagioclase rock. A little bit of garnet. It's a metamorphic rock. All that lithium had diffused from a fluid into the crystal. And lithium diffusion is really, really fast. So there are dispersion halos around pegmatites, and they can be used as exploration vectors. There's you see a metavolcanic rock or a gabbro that's running a few hundred ppm lithium. It's like, sure as heck didn't come from the gabbro. It came from a fluid. So the hydrothermal processes aren't really important as ore forming processes, but they are important in terms of creating vectors for mineralization. And this is a picture of me at Bagno in May, which is a pretty spectacular pegmatite with nice little spodumene crystals. Thank you very much.